History of Java. Java, one of the most widely used programming languages, has a rich history that spans over 2 decades. Its journey from a simple language designed for interactive television to becoming the backbone of enterprise applications, Android development, and more is a fascinating story. 1. The birth of Java, 1991 to 1995. Java began in 1991 as part of a project initiated by James Gosling, Mike Sheridan, and Patrick Naughton at Sun Microsystems. The project, initially called the Green Project, aimed to create a language for programming consumer electronics like set-top boxes. However, as the team realized the potential of the language they were developing, their focus shifted toward creating a new platform-independent language that could be used on various devices. In 1995, Java was officially released, and it quickly gained popularity due to its write once, run anywhere (WORA) capability. This meant that Java programs could run on any device with a Java Virtual Machine (JVM), making it highly versatile and attractive to developers. 2 early development and versions, 1996 to 2004. Java's first major version, Java 1.0, was released in 1996. It included core features such as the JVM, basic APIs, and the concept of applets, which allowed small Java programs to run in web browsers. Java 1.1, released in 1997, brought significant improvements, including inner classes, JavaBeans, and JDBC, Java Database Connectivity. The late 1990s and early 2000s saw Java's rapid growth. Sun Microsystems released Java 2 in 1998, which marked a major overhaul of the language and its runtime environment. Java 2 was divided into 3 platforms: J2SE, Standard Edition, J2EE, Enterprise Edition, and J2ME, Micro Edition. These versions catered to different application domains, from desktop applications to large-scale enterprise systems and mobile devices. 3. Java's rise to prominence, 2004 to 2010. In 2004, Java 5, also known as Java 1.5, was released, introducing significant language enhancements such as generics, annotations, enumerations, and the enhanced for loop. These features made Java more powerful and easier to use, solidifying its position as a leading language for enterprise development. Java 6, released in 2006, focused on performance improvements, better web services support, and enhancements to the JVM. During this period, Java became the go-to language for large-scale enterprise applications, particularly with the widespread adoption of the J2EE platform. For the Oracle acquisition and modern Java, 2010-present. In 2010, Oracle Corporation acquired Sun Microsystems, taking over the development of Java. This period marked a new era for the language, with Oracle driving its evolution and adoption in new domains. Java 7, released in 2011, introduced Project Koin, which included small language changes aimed at making the language more user-friendly. Java 8, released in 2014, was a landmark version that introduced Lambda expressions, the Stream API, and the new DateTime API, significantly modernizing the language. Java 9, released in 2017, introduced the module system, Project Jigsaw, which allowed developers to create modular applications and improved the structure and maintainability of large projects. Subsequent versions, including Java 10 through Java 16, saw Oracle adopting a new release cadence, with new versions being released every 6 months. 5. Java in modern development. Java continues to be a dominant language in many areas of software development. It's the foundation of Android development, where it powers millions of mobile applications. In the enterprise world, Java remains a key language for developing large-scale systems, with frameworks like Spring making it easier to build robust and scalable applications. Java has also found its place in cloud computing, big data, and the Internet of Things, IoT. Its versatility and the vast ecosystem of libraries and tools available have ensured its continued relevance in an ever-evolving tech landscape. 6. The future of Java. Java's future looks bright as it continues to evolve with the needs of modern software development. With a strong community, ongoing updates, and a focus on maintaining backward compatibility, Java is well positioned to remain a cornerstone of the software industry for years to come. Explain Java. Java is a high-level, object-oriented programming language that was originally developed by Sun Microsystems in the mid-1990s and is now maintained by Oracle Corporation. It's one of the most widely used programming languages in the world, known for its portability, scalability, and reliability. Here's an overview of what Java is and its key features. 1. High-level language. Java is a high-level language, which means it's designed to be easy for humans to read and write. It abstracts away much of the complexity of the underlying hardware, allowing developers to focus on building applications without needing to manage memory directly or deal with low-level operations. 2. Object-oriented programming, OOP. Java is an object-oriented programming language, meaning it follows the principles of OOP. This paradigm organizes software design around data, or objects, rather than functions and logic. Key concepts in OOP include classes and objects. A class is a blueprint for creating objects, which are instances of classes. Inheritance. Classes can inherit properties and methods from other classes, promoting code reuse. Polymorphism. Objects can be treated as instances of their parent class, allowing for flexible and dynamic code. Encapsulation. Data and methods are encapsulated within objects, protecting the internal state and promoting modularity. 3. Platform independence. Write once, run anywhere. One of Java's most famous features is its platform independence, often summarized by the phrase, write once, run anywhere, WORA. This means that Java code, once compiled, can run on any device that has a Java Virtual Machine, JVM. The JVM interprets the compiled Java bytecode into machine-specific instructions, making it possible to run the same Java program on different platforms, Windows, Mac OS, Linux, etc., without modification. 4. Java Virtual Machine, JVM. The JVM is a key component of the Java platform. It provides an environment in which Java bytecode can be executed. The JVM is responsible for memory management, garbage collection, and the conversion of bytecode into machine code. The JVM makes Java programs portable across different operating systems and hardware architectures. 5. Garbage collection. Java automatically manages memory through a process called garbage collection. This means that Java automatically recycles memory that is no longer in use, freeing developers from the need to manually allocate and deallocate memory, reducing the likelihood of memory leaks and other related bugs. 6. Rich standard library. Java comes with a comprehensive standard library, also known as the Java API, which provides a wide range of pre-built classes and methods that developers can use to perform common tasks. These include data structures, classes for handling data types like arrays, lists, sets, and maps. I/O operations, tools for reading and writing data to files, databases, and other sources. Networking, libraries for building networked applications, including support for HTTP, TCP/IP, and more. Concurrency, built-in support for multi-threading and concurrent programming. User interface, tools like Swing and JavaFX for building graphical user interfaces, GUIs. 7. Security. Java was designed with security in mind. The language includes several features to help protect applications from threats such as bytecode verification. The JVM checks the bytecode for illegal code that could violate access rights. Security Manager. Java provides a security manager that defines what resources a class can access, such as reading from or writing to the local disk. Sandboxing. Applets, small Java programs that run in web browsers, are executed in a restricted environment to prevent them from harming the user's system. 8. Multithreading. Java has built-in support for multithreading, which allows multiple threads, independent paths of execution, to run concurrently within a single program. This is useful for building applications that can perform multiple tasks at the same time, such as handling user input while processing data in the background. 9. Portability and scalability. Java is known for its portability across different platforms and its ability to scale from small applications to large enterprise systems. The combination of the JVM and Java's platform-independent bytecode ensures that Java applications can be easily moved from one system to another. Additionally, Java's architecture and libraries make it suitable for a wide range of applications, from desktop software to large distributed systems. 10. Community and ecosystem. Java has a large, active community of developers and a rich ecosystem of tools, frameworks, and libraries. This support makes it easier to find resources, get help, and integrate Java into various development environments. Popular frameworks like Spring, Hibernate, and Apache Kafka have made Java a leading choice for building web applications, microservices, and big data solutions. 11. Application domains. Java is used in various domains, including enterprise applications. Java is widely used in the enterprise for building large-scale, distributed systems, often leveraging the Java Enterprise Edition, Java EE, platform. Mobile applications. Java is the primary language for Android development, making it crucial for mobile app development. Web applications. Java is often used to develop dynamic web applications, using frameworks like Spring MVC, Struts, and JSF, Java server faces. Embedded systems. Java is also used in embedded systems, particularly with Java ME, Micro Edition. What is Java? Java is a high-level, object-oriented programming language designed to be platform-independent, meaning that programs written in Java can run on any device or operating system that has a Java Virtual Machine, JVM. This, write once, run anywhere, capability is one of Java's most well-known features. Key features of Java. Object-oriented. Java is based on the principles of object-oriented programming, OOP, which organizes software design around data, or objects, rather than functions and logic. It supports key OOP concepts like classes, objects, inheritance, polymorphism, and encapsulation. Platform independence. Java code is compiled into an intermediate form called bytecode, which is executed by the JVM. This allows the same Java program to run on different platforms without modification, making it highly portable. Robust and secure. Java has built-in security features and robust error handling mechanisms, making it a reliable choice for developing secure applications. The language also includes automatic memory management through garbage collection, which helps prevent memory leaks and other common programming errors. Multithreading. Java supports multithreading, allowing multiple threads, independent paths of execution, to run simultaneously within a program. This is useful for developing applications that need to perform multiple tasks at once, like handling user input while processing data. Rich standard library. Java comes with a comprehensive set of libraries, Java API, that provide tools for everything from data structures and algorithms to network communication and user interface development. Versatile use cases. Java is used in a wide range of applications, including web development, mobile apps, especially Android, enterprise software, and even embedded systems. Its versatility has made it one of the most popular programming languages worldwide. How Java works. Java source code. Developers write Java programs in plain text files with a .java extension. Compilation. The Java compiler, JAVAC, converts the source code into bytecode, which is saved in files with a .class extension. Execution. The JVM reads the bytecode and translates it into machine code specific to the underlying hardware, allowing the program to run on any device with a JVM. Java ecosystem. Java SE, Standard Edition provides the core functionality for general-purpose programming. Java EE, Enterprise Edition extends Java SE with specifications for enterprise features such as distributed computing and web services. Java ME, Micro Edition designed for embedded systems and mobile devices. What are the differences between C++ and Java? C++ and Java are both powerful, high-level programming languages, but they differ in many ways due to their design philosophies, use cases, and features. Here's a comparison of the two. 1 language type. C++. C++ is a statically typed, compiled language that supports both procedural and object-oriented programming. It also allows for low-level memory manipulation, which gives developers more control over system resources. Java. Java is a statically typed, interpreted language that is purely object-oriented, with some exceptions for primitive data types. It emphasizes portability and security, with no direct memory manipulation. 2. Memory management. C++. In C++, memory management is manual. Developers use pointers and allocate/deallocate memory using new, delete, and other functions. This provides flexibility but also increases the risk of memory leaks and pointer errors. Java. Java handles memory management automatically through garbage collection. The JVM automatically deallocates memory that is no longer in use, which reduces the risk of memory leaks and makes development easier but can result in less precise control over system resources. 3. Platform independence. C++. C++ code is compiled into machine code that is specific to the operating system and hardware. This means that C++ programs need to be recompiled for each platform. Java. Java code is compiled into bytecode, which is executed by the Java Virtual Machine, JVM. This allows Java programs to run on any platform with a JVM, making Java inherently platform independent. 4. Performance. C++. C++ generally offers higher performance because it is compiled directly into machine code, and developers can optimize the code to interact directly with hardware. It's often used in applications where performance is critical, like game development, systems programming, and real-time systems. Java. Java typically runs slower than C++ because the JVM interprets bytecode at runtime, adding an extra layer of abstraction. However, Java's performance has improved significantly with advancements like just-in-time, JIT, compilation. 5. Syntax and complexity. C++. C++ syntax is more complex due to features like pointers, multiple inheritance, operator overloading, and templates. This complexity allows for powerful, fine-grained control but can make the language harder to learn and debug. Java. Java has a simpler syntax compared to C++. It does not support pointers, multiple inheritance, in the class hierarchy, or operator overloading, which reduces complexity and makes Java easier to learn and use. 6. Object-oriented programming. C++. C++ is a multi-paradigm language that supports both procedural and object-oriented programming. It allows for features like multiple inheritance and function overloading. Java. Java is designed to be a purely object-oriented language, with some exceptions, like primitive data types. It does not support multiple inheritance directly but uses interfaces to achieve similar functionality. 7. Use cases. C++. C++ is widely used in systems programming, game development, real-time systems, embedded systems, and applications where performance and low-level resource management are critical. Java. Java is commonly used in enterprise applications, web applications, Android development, cloud-based services, and large-scale systems where portability and ease of maintenance are important. 8. Exception handling. C++. C++ supports exception handling, but it's less emphasized and can be bypassed. The language allows for more traditional error handling approaches like return codes. Java. Java has a robust and mandatory exception handling mechanism, making it integral to the language. Every checked exception must be either caught or declared to be thrown, encouraging developers to handle errors consistently. 9 standard libraries and ecosystem. C++. C++ has a rich standard template library, STL, that provides powerful data structures and algorithms, but it lacks a comprehensive built-in framework for things like GUIs, networking, or database access. Developers often rely on third-party libraries. Java. Java comes with an extensive standard library, Java API, that includes everything from data structures to networking, GUIs, and more. This makes Java well suited for a wide range of applications out of the box. 10. Concurrency and multithreading. C++. C++ supports multithreading, but it requires more manual management of threads and synchronization, often relying on third-party libraries or platform-specific features. Java. Java has built-in support for multithreading and concurrency, with a comprehensive set of utilities and classes that simplify thread management, synchronization, and concurrent programming. List the features of Java programming language. Java is a widely used programming language that comes with several key features. Here's a list of the main features that make Java popular. 1. Object-oriented. Java is an object-oriented programming language, which means it is based on the concept of objects. Everything in Java is an object, which allows for modular, reusable code. Java supports the key principles of object-oriented programming: inheritance, encapsulation, polymorphism, and abstraction. 2. Platform independent. Java is known for its platform independence, which is achieved through the use of the Java Virtual Machine, JVM. Java code is compiled into bytecode, which can be executed on any device with a JVM, regardless of the underlying hardware or operating system. This is often summarized by the phrase, write once, run anywhere, WORA. 3. Simple. Java was designed to be easy to learn and use. Its syntax is straightforward, especially for those familiar with C or C++. It removes complex features like pointers, operator overloading, and multiple inheritance, which simplifies the programming process. 4. Secure. Java provides a secure programming environment through several features. Bytecode verification ensures that the code adheres to Java's security constraints. Security Manager defines the access levels of classes. Automatic memory management. Java's garbage collector prevents memory leaks and other common programming errors. 5. Robust. Java is designed to be reliable, with strong memory management and error handling. It eliminates issues such as memory leaks and invalid memory accesses through its automatic garbage collection and strong type checking at both compile time and runtime. 6. Multi-threaded. Java supports multithreading, allowing the development of applications that can perform multiple tasks simultaneously. Java's built-in thread management allows developers to build interactive and responsive applications. 7. High performance. Although Java is an interpreted language, its performance is enhanced by just-in-time JIT compilers, which compile bytecode into native machine code at runtime. This allows Java to achieve near-native performance levels. 8. Distributed. Java was designed with networking in mind. It includes a vast set of libraries for developing distributed applications. Java supports technologies like remote method invocation, RMI, and Corba, making it easier to create distributed systems. 9. Dynamic. Java is considered dynamic because it can adapt to an evolving environment. Java supports dynamic loading of classes, meaning new code can be added to a running Java program without interrupting the process. Additionally, Java can perform runtime type checking. 10. Portable. Java's portability is one of its standout features. Java programs are platform independent at both the source and binary levels, thanks to the JVM. This means Java applications can run on any device that has a JVM installed, without requiring any modification to the code. 11. High-level abstraction. Java provides high-level abstraction from hardware details, allowing developers to focus on programming rather than on the underlying system architecture. This abstraction simplifies development and makes code easier to write, read, and maintain. 12. Extensive standard library. Java comes with a rich standard library, Java API, which provides a vast array of classes and methods for common programming tasks such as data structures, networking, input/output operations, user interface development, and more. 13. Architecture neutral. Java's design ensures that the size of its primitive data types remains consistent across all platforms. This consistency contributes to Java's platform independence, making the language architecture neutral. 14. Backward compatibility. Java strives to maintain backward compatibility, meaning that newer versions of Java can run code written in older versions without modification. This protects the investment in existing Java code bases. 15. Community support. Java has a large, active community that continuously contributes to its development, making it easier to find support, libraries, frameworks, and tools. This community-driven ecosystem enhances Java's capability and longevity. What do you understand by Java Virtual Machine? The Java Virtual Machine, JVM, is a crucial component of the Java programming language's architecture. It is an abstract computing machine that enables a computer to run Java programs, making Java platform independent. Here's a detailed explanation of the JVM. 1. Role of the JVM. Execution of Java programs. The primary role of the JVM is to execute Java bytecode, which is the intermediate code generated by the Java compiler from the source code. The JVM translates this bytecode into machine code specific to the host system, allowing the program to run on any platform with a compatible JVM. Platform independence. The JVM is what gives Java its platform-independent nature. Java code is compiled into bytecode, which is not specific to any operating system or hardware. This bytecode can be executed on any device that has a JVM installed, regardless of the underlying architecture. 2. JVM architecture. The JVM is made up of several components that work together to execute Java programs. Class loader. The class loader loads the Java classes into the JVM at runtime. It handles the loading, linking, and initialization of classes, ensuring that the necessary classes are available for execution. Bytecode verifier. Before execution, the bytecode verifier checks the loaded bytecode for correctness and security violations. It ensures that the bytecode adheres to Java's safety constraints, preventing dangerous operations like illegal memory access. Interpreter. the interpreter reads the bytecode and executes it instruction by instruction. In some cases, this can lead to slower performance, which is why the JVM often uses just-in-time JIT compilation to optimize execution. Just-in-time JIT compiler. The JIT compiler translates bytecode into native machine code at runtime, which significantly improves the performance of Java applications. The JIT compiler identifies frequently executed code, hotspots, and compiles them into machine code to speed up execution. Garbage collector. The garbage collector is responsible for automatic memory management within the JVM. It identifies and removes objects that are no longer in use, freeing up memory and preventing memory leaks. Java Native Interface, JNI. JNI is a framework that allows Java code running in the JVM to interact with native applications or libraries written in other languages like C or C++. This is useful for accessing platform-specific features that are not available in the Java standard library. 3. JVM lifecycle. Loading. The class loader loads the .class files, bytecode, into memory. Linking. The linking process involves verifying, preparing, and resolving the loaded classes. Initialization. The JVM initializes the class variables and invokes the main method to start the execution of the program. Execution. The JVM executes the bytecode using the interpreter or JIT compiler. The execution phase continues until the program terminates, either normally or due to an exception. Shutdown. Once the program execution is complete, the JVM performs cleanup operations, including the final garbage collection, before shutting down. 4. JVM languages. Java. While Java is the most common language executed by the JVM also supports several other languages. Examples include Kotlin, a modern language that is fully interoperable with Java and also runs on the JVM. Scala, a language that combines object-oriented and functional programming paradigms, running on the JVM. Groovy, a dynamic language for the JVM that integrates smoothly with Java. Clojure, a functional, dynamic language that runs on the JVM. 5. Platform independence. The JVM's ability to run the same bytecode on any platform without modification is what makes Java a write once, run anywhere language. This platform independence is one of Java's most significant advantages. 6. JVM implementations. There are various implementations of the JVM, including Hotspot, the default JVM implementation provided by Oracle's JDK. It's known for its efficient garbage collection and JIT compiler. OpenJ9, an open-source JVM implementation that focuses on performance and memory footprint, developed by the Eclipse Foundation. GraalVM, a JVM that supports polyglot programming, allowing for the execution of languages other than Java, like JavaScript, Python, and Ruby, in the same runtime environment. 7. Security. The JVM includes several security features, such as the sandboxing of code, which restricts the execution of potentially harmful operations, and the bytecode verifier, which ensures that the bytecode adheres to Java's security constraints. What is the difference between JDK, JRE, and JVM? 1. Java Development Kit, JDK. Definition. the JDK is a full-featured software development kit used for developing Java applications. It includes everything needed to compile, debug, and run Java programs. Components. Java compiler. Javac. The compiler converts Java source code, .java files, into bytecode, .class files, which can be executed by the JVM. Java Runtime Environment, JRE. The JDK includes the JRE, which contains the necessary libraries and JVM to run Java applications. Development tools. The JDK comes with a set of tools for development, such as Javac, compiler, Javadoc, documentation generator, JDB, debugger, and others. Libraries. The JDK includes a collection of Java standard libraries, APIs, that are used to develop Java applications. Purpose. The JDK is primarily used by developers to write, compile, and debug Java applications. To Java Runtime Environment, JRE. Definition. The JRE is a subset of the JDK and provides the environment required to run Java applications. It includes the JVM and a set of libraries that support the execution of Java programs. Components. Java Virtual Machine, JVM. The JVM is part of the JRE and is responsible for executing Java bytecode. Core libraries. The JRE includes core libraries that provide essential functionality to Java programs, such as I/O operations, networking, data structures, etc. Other components. The JRE also includes runtime libraries, class loaders, and other components necessary for running Java applications. Purpose. The JRE is used by end users and developers to run Java programs. It does not contain the development tools found in the JDK, so it is not suitable for writing Java applications. 3. Java Virtual Machine, JVM. Definition. The JVM is an abstract machine that provides the runtime environment in which Java bytecode is executed. It is platform independent, meaning that the same Java program can run on any platform that has a compatible JVM. Components. Class loader. The class loader loads class files into the JVM. Bytecode verifier. The bytecode verifier checks the bytecode for illegal code that could violate access rights to objects. Execution engine. The execution engine interprets and executes the bytecode. It can use the just-in-time JIT compiler to convert bytecode into native machine code for faster execution. Garbage collector. The garbage collector automatically manages memory, freeing up memory that is no longer in use. Purpose. The JVM is the engine that runs Java applications. It takes the compiled bytecode and converts it into machine code that the host system can execute. Key differences.